Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about evaluating limits.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. The limit as x approaches 2 of f of x, where f of x is equal to the piecewise function negative x squared plus 2 when x is not equal to 2, and negative 5 when x is equal to 2. And we have to find this limit. So we have our graph right here that graphs this piecewise function. Notice on the graph, we have a parabola, right? That's a frown in a way. But then there's an open hole right there where at x equals 2, it jumps down to a point where the y value is negative 5, okay? Now when we take the limit as x approaches 2, we need to see where is it approaching from the left and right. And it's not equal to when x equals 2, but it's what it's approaching as we get close to a positive 2. And so with that graph, you can see that it's actually approaching the value that would be the first part of the equation, the negative x squared plus 2. And so we use this part to evaluate what happens at 2, and then that's going to be our limit where it's approaching. Also because this is a continuous function except at x equals 2. Okay, so what we do is we say, all right, what happens if we put a 2 in for our x for the top equation? So we have negative 2, and that's going to be square, and the negative out front, plus 2. Then we simplify this. Negative 2 squared is a positive 4, but don't forget the negative that's out front, plus 2. Negative 4 plus 2 is a negative 2. And so we would say that this limit as x approaches 2 of f of x is equal to a negative 2, and that is our final answer. We're given this limit right here, the limit as x approaches negative 2 of a negative, and then the fraction here, x squared minus 4 over x plus 2, and we have to evaluate this limit. Now we're given a graph right here of this limit. Now notice, well, the function, but notice it's really a linear line, right? Straight line. But there's an open hole right there at negative 2. So that's really showing here that this rational function can't exist at negative 2. We can't just plug it right in. Negative 2 right here in x would cause the denominator to equal 0. So we have to find a way to simplify this. Now the numerator looks like it can factor. Let's try that. So again, we have to write out the limit as x approaches a negative 2 of our numerator, which, well, can it factor? What two numbers multiply by negative 4, but add to the b value 0, and we have a plus 2 and a minus 2. And a good tip when you see problems like this, always think it's probably something in the denominator that will cancel out. So we have a plus 2, minus 2 going on there, and look, we can cancel out right here. So we can cancel out the x plus 2, so we have a limit now as x approaches a negative 2 of a negative, just the numerator, x minus 2. And at this point, we can take the limit. We can take the limit by plugging negative 2 in, because this now will exist everywhere. Negative 2 in for x, so we have a negative, negative 2, minus 2, and again we plug that negative 2 in, right there. Negative 2 minus 2 is a negative 4, and then a negative 4 is a positive 4. And so the final answer, this limit, is equal to positive 4. We're given this problem right here, the limit as x approaches 3 of x squared minus 7x plus 12 all over x minus 3. And we have to, well, solve this limit. Now, one thing I noticed here, we can graph this function, and if we graph the x squared minus 7x plus 12 over x minus 3, we can see that here on our graph. Now it's a linear line going through, but we have an open hole, open circle there at a positive 3, which makes sense, or an x is positive 3. Makes sense because here, well, we have x is at positive 3, our denominator is equal to 0. So we can obviously try to solve this by looking at the graph, and to be honest, it'll be negative 1. It's approaching negative 1, the y value from left and right. But let's show it algebraically, because that's what we want to evaluate here. So to do that algebraically, what we want to do is we want to see if we can, well, simplify this limit, right? We're going to factor the numerator here. So we have the limit here as x approaches 3 of our numerator, and we want to see if that can factor. And the goal there is to see if one of them is, well, an x minus 3. And it actually is, and that's always a good telling point here. We have an x minus 3 here, and x, and what two numbers multiply to be positive 12, but add to be a negative 7, x minus 3, x minus 4. X minus 3's will cancel, and so we're left with now the limit as x approaches 3 of just what's left, x minus 4. Now we can evaluate this limit. Let's put 3 in for x. We have a 3 now minus 4, and a 3 minus 4 is a negative 1. And so like I said, our limit here is equal to a negative 1. We're given this problem right here, the limit as x approaches negative 3 of an x plus 3 over an x squared plus 2x minus 3. We get to evaluate this limit. Now we can graph this limit. We can see the graph right here, but that's just we're going to use that and then try to solve it algebraically. So if we look at the graph here, what happens at negative 3? Well, we have a open circle there at negative 3, meaning that at some value for x, when we plug in the denominator, it will cause the denominator to equal 0, and we can't have that limit there. The value exists there. So what I'm going to do is see if we can simplify this function that we're taking the limit of and see if we can cancel something out there. So let's redo this limit as x approaches a negative 3, and we're going to factor the denominator. Makes it easy. Well, two numbers multiply to be negative 3, but add to be a positive 2, and that's a positive 3 and a negative 1. That helps us here because we can see the x plus 3 is going to cancel. So what happens now, we have the limit as x approaches a negative 3 of 1 over an x minus 1. Now, we can now plug negative 3 in for x to find this limit, all right, because it will exist there. So to do that, we have 1 over a negative 3 in for x minus 1. And we keep on going. 1 over, well, negative 3 minus 1 is a negative 4. Put a 4 here, put the negative out front. And so this kind of matches up with our graph, but our final answer for this limit is a negative 1/4. We're given this limit right here, the limit as x approaches 0 of f of x, where f of x is equal to the piecewise function x plus 1, where x is not equal to 0, and 2 when x is equal to 0. And we have to find the limit. Now one thing I'm noticing here about this limit, it says when x is approaching 0. Well, we have two things that happen here. Our first equation says it happens everywhere except for when x is equal to 0, so x cannot equal 0 here, and this only happens when x equals 0. Now our idea with limits is where it's approaching, alright, so what happens when this function is approaching 0 from the left and the right? Well, with that we would have to deal to the first function. We're not finding when it's equal to 0, but when it's approaching, and on all other values it's approaching x equals 0, we use this first part of the function. So with that being said, we look at that, we're going to plug 0 in. 0 in for x plus 1, pretty simple here. 0 plus 1 is 1. So we would say that this limit, as x approaches 0, of our function f of x is equal to 1, and that's our final answer. We're given this problem right here, the limit as x approaches 3 of f of x, where f of x is equal to the piecewise function 2 plus x over 2, where x is not equal to 3, and a 2 when x is equal to 3. We have to find the limit. Now, it tells us here we find out where x is approaching 3. And this is the thing that everyone gets confused on. When it's approaching 3, it isn't exactly where it's equal to 3. Where it's equal to 3 is right here at 2. But when it's approaching 3, we actually have to use the top equation because any other x value is approaching, right? It's approaching when x equals 3, we use the top equation. It's approaching from the left and right there. So we have to use our top equation here. We're going to plug 3 into that top equation. 2 plus 3 over 2. And now we're going to, well, solve for that. 2 can be written as a fraction as 4 halves plus 3 halves. 4 halves plus 3 halves comes out to be a 7 halves. So again, we need to find this limit as x approaches 3 of f of x. Let's relabel it. And it's equal to, again, that 7 halves. It's where it's approaching, not what it's equal to. So our limit here is equal to 7 halves, and that's our final answer. We're given this problem right here, the limit as x approaches 1 of a negative x squared minus 1 over x minus 1. And again, we're finding this limit. When we see limits like this, right away, we can't just plug in 1 to be x because, well, it would be divided by 0. All right? So with rational functions, we're going to try to simplify this. And a lot of it involves factoring. So I see the top part can factor, so I'm going to factor that top part. So again, we write the limit as x approaches 1 of a negative, and we're going to try to factor that numerator. That's going to be over the x minus 1. Most likely, the x minus 1 is being one of the factors. And in reality, the top part factors to be x minus 1 and x plus 1. We can see the x minus 1's cancel, and so if I put that down here, we have the limit now as x approaches 1 of a negative, in parentheses, just that x plus 1 part. It's at this point we can take the limit. So if we take the limit, we can put the 1 in for the x, and we have a negative 1 plus 1. And if you want to put a parenthesis to show you substituted it in. And then we keep simplifying, really. 1 plus 1 is a 2. Your negative is out front. And so our limit here and final answer is just a negative 2. We're given this limit right here. The limit as x approaches 5 of a negative, and then rational function x squared minus 5x over x minus 5. Well, first thing I'm looking here with a rational function, I'm going to try to, well, factor this and see if we can simplify it. Because right now, I can't plug a 5 in because the denominator equals 0, and we can't really figure out what that value is. So what I'm going to do is take the limit again as x approaches 5, but we're going to factor that numerator out. Now, this one's actually not a full, well, it's a factor, but we can see there's an x in both parts. So we pull out the x here, we're left with an x minus 5. And that's what we're really looking for. The x minus 5s can cancel. We're trying to get something out of that denominator. So, with that being said, we have the limit here as x approaches 5 of just a negative x value. And it's at this point we can take that limit. When we take that limit, we can plug a 5 in for that x, and we get our answer actually, which is negative 5, which maybe isn't the best thing to put down here. I could have put it there, but it's all good. So our final answer here for this limit is a negative 5. We're given this problem right here, the limit as x approaches 2 of a negative x squared minus x minus 2 over x minus 2, and we want to evaluate this. Whenever I see limits like this, I'm always looking for how can I maybe factor to cancel something out of the denominator. Because in reality here, we put a 2 in the denominator, it's dividing by 0. That's an issue. So we're going to retake this limit as x approaches 2, if I can write that, and we're going to factor out the numerator, or factor the numerator. Okay? And most likely, in most of these cases, it'll factor to be something that cancels out in the denominator. Well, we factor the numerator, and I'm going to go ahead and just put that there. What two numbers multiply to be negative 2, but add to be a negative 1, x minus 2 and x plus 1. Now from here, we see x minus 2's cancel. So we're left with now the limit as x approaches 2 of a negative x plus 1. It is at this point we're allowed to actually take that limit. We can plug 2 in for x because it's a continuous function and exists there. Put a negative now, 2 plus 1, and we're solving. Pretty easy. 2 plus 1 is 3, negative out front, and negative 3. And so my final answer here is just a negative 3. We're given this problem right here, the limit as x approaches negative 5 of x squared plus 3x minus 10 over an x plus 5. We got to evaluate this. Now, one thing I like to do with a rational function is I'm trying to factor the numerator to cancel out something in the denominator. Because as you can see, a negative 5 goes in for x here in the denominator, and we're dividing by 0. So, let's try to factor that numerator. Let's rewrite the beginning part. Then, okay, the numerator, can we factor this? Well, what two numbers multiply to be negative 10, but add to be positive 3? And that's a positive 5 and a minus 2. Which is good, because we want the x plus 5 to cancel out, which it does. X plus 5's cancel here, and we're left with now the limit as x approaches a negative 5 of that x minus 2 that's in the numerator. It is at this point we can take the limit. Put a negative 5 in for x, and we minus a 2, and negative 5 minus 2 is a negative 7. And so my final answer for this limit is a negative 7. We're given this limit right here. The limit as x approaches 0 of 1 over negative 4 plus x plus 1/4 all over x. And we got to evaluate this limit. One thing we know right off the bat, 0 in for x causes some issues. We cannot divide by 0. So I'm going to try to rearrange, combine these fractions, and maybe we can do something that simplifies and crosses out this x down here. So to do that, I'm going to multiply this part here by a 4 over 4. And the second fraction, to find a common denominator, an x minus 4 over itself. Notice, parentheses here, negative 4 plus x is the same as x minus 4. So let's take that limit, move the limit here, as x approaches 0. And on the numerator, we have a 4 plus 1 times x minus 4, which is an x minus 4. And the denominator is the 4 times an x minus 4, and that's all over that good old x here. Now, this is pretty nice. These 4's cancel, right? So what do we have? Let's rewrite it here. We have the limit as x approaches 0 of that numerator, x over a 4x minus 4, and that's divided by x. And I'm going to write that like this. Divided by x makes it a little easier to see. Well, we keep taking that limit as x approaches 0 of x over 4 times an x minus 4. And instead of dividing by x, let's multiply by 1 over x. Remember, same thing. This makes it easier to see that these x's cancel. So we're now left with the limit as x approaches 0 of 1 over 4 times a x minus 4. Well, at this point, our rational function only doesn't exist when, when the denominator is equal to 0. And 0 goes in, we're good. So now we can take that limit. We plug 0 in for x. We have 1 over 4 times 0 minus 4. Well, 0 minus 4 is a negative 4, so we have 4 times a negative 4. And 4 times a negative 4 is a negative 16. So we have 1 over we'll put a negative over here, a negative 1/16, and that is our final answer. We're given this problem right here. The limit as x approaches negative 3 of x over a 1 over 3 plus x minus 1/3. And we had to find this limit. Now the first thing I'm going to try to do is see if we can combine this fraction down here. Okay? We really have to simplify this to try to cancel something out. Because right now we have an issue. Negative 3 goes right in for that x, and we're dividing by a 0. And so we can't do that. So to find a common denominator, I'm actually going to multiply this fraction by a 3 over 3, if you can see that, right here. Because that's this denominator, and this one I'm going to multiply a x plus 3 over an x plus 3. It's the same thing as a 3 plus x. So now let's go see what happens when we do that. We have the limit as x approaches a negative 3 of x over. Now notice we'll have the same denominator, 3 times an x plus 3. The numerator is just a 3 minus this x plus 3, like so, because 1 times x plus 3 is x plus 3. Now hopefully you can see this here, but that negative sign, if we bring it into both parts, we have a negative x and a negative 3 here. These will cancel. And so we're left with now the limit as x approaches a negative 3 of x over a negative x over a 3x plus 3. So now what we're going to do is we're going to take this and we're going to kind of rearrange that division. I don't like the multiple division stuff. What does that equal here? Well, this limit as x approaches a negative 3 is equal to, all right, if we put the x out here, that first one, and instead of dividing by this fraction, we multiply by the reciprocal. Multiply by a 3x plus 3 over a negative x. And what this allows me to do is cancel out these x values. So we're left with the limit as x approaches a negative 3 of a negative, don't forget that down here, 3x plus 3. And now we can evaluate the limit right there at negative 3. We can plug it in. Negative 3 times a negative 3 goes in, plus 3. Well, negative 3 plus 3 is just a 0. So negative 3 times 0, you guessed it, is 0. And so my final answer here for this limit is 0. We're given this problem right here, the limit as x approaches 5 of x minus 5 over the square root of x plus 4 minus, well, 3 outside the square root. We're evaluating this limit. Now, we can't evaluate right as x equals 5. 5 goes in the denominator here. For x, square root, 5 plus 4 is 9, square root of 9 is 3, and we get 0 in the denominator. So I'm going to try to get rid of that square root and see if I can, do something with it. And this is what I'm going to do. I'm going to multiply this by the conjugate, the square root of x plus 4 plus 3 over itself. And this is a common technique here with square roots. And so what this allows me to do, we're going to take the limit again, make sure we show this. For the denominator, right, we multiply this square root of x plus 4 times the square root of x plus 4, and that's just equal to an x plus 4. The inside parts, when we FOIL, eliminate with the minus 3 plus 3, and negative 3 plus 3 is a negative 9. Well, when you multiply them. The numerator, we still have that x minus 5. I'm going to leave it like this, times the square root of x plus 4 plus 3. Let's keep writing this out. The limit here, as x approaches 5, of our denominator simplifies, 4 plus or minus 9 is a negative 5. We have an x minus 5 in the denominator. Numerator is still that x minus 5 times the square root of x plus 4, and we have the plus 3. I always forget to make it long enough. Well, look, x minus 5's cancel. That's what we're looking for. So let's go rewrite this limit as x approaches 5 of the square root of an x plus 4 plus 3 that's left over. And now, at this point, we can take the limit. We can plug 5 right in for x. So we have the limit here as x approaches 5 of, 5 plus 4. Oops, don't need that extra parenthesis. And then plus 3. Oh, and at that point, actually, we're taking the limit. I don't need to write limit anymore. Ignore that extra space. 5 plus 4 is 9. Square root of 9 plus 3. And square root of 9 is a 3. So 3 plus 3 is a good old 6. And there we have it. Our final answer here for our limit is 6. We're given this problem right here. The limit as x approaches 3 of the square root of x plus 6, then minus a 3, all over x minus 3. And we're going to evaluate this limit. What I like to do when I see square roots and we try to cancel something out, I'm going to multiply this by its conjugate. And we have to because we can't just plug 3 into the denominator because we're dividing by 0. So I'm going to multiply this by its conjugate, which is the x plus 6 plus a 3 over itself. Put some parentheses, make it a little easier. So what happens when we do this? Well, we take the limit as x approaches 3, and the numerator, x plus 6, square root of x plus 6 times square root of x plus 6 is just the x plus 6 here. The middle parts, when we FOIL, cancel out, and so we just do the negative 3 times a 3, which is a negative 9. All of that is over, and we're going to keep the denominator as is. X minus 3 times the square root of x plus 6 plus 3. Now this numerator we can simplify a little more, right? 6 minus 9 is a minus 3. So we have the limit here as x approaches 3 of, just an x minus 3 over, and here's a duplicate, x minus 3, and then the square root of x plus 6 plus 3. Just within space, I think. Okay. Well, the x minus 3's will cancel. So now, I know, a lot of work for these limits. The limit as x approaches 3 of 1 over the rest of that denominator, the square root of x plus 6 plus 3. And at this point, we can plug 3 directly in for x to solve this limit. So we have 1 over the square root of 3 plus 6, and we're plugging that 3 in. And then we have plus 3 over here. Keep simplifying. 1 over, well, 3 plus 6 is 9. Square root of 9 plus 3. Square root of 9 is 3. And 3 plus 3 is 6. So we have a 1 over 6 here. And so our final answer is this limit is equal to 1/6. We're given this critical thinking question. Give an example of a limit of a rational function where the limit at -1 exists, but the rational function is undefined at -1. So first I'm starting off with, well, the limit has to exist, or we defined it at -1. That's really what's going on. So we're taking the limit as x approaches a -1. Now, what happens where it's undefined at -1? Well, if I have just an x plus 1 in the denominator here, at -1 plug in will be undefined, right? Because -1 goes in for x, and we're dividing by 0. But eventually, I'm going to want this to cancel out that x plus 1, so it would exist. So we put an x plus 1 in the numerator. Then, we have to add something else to this, right? So we want it to exist at -1, so let's go put in x minus 1 up top. And so we can see this limit here, -1 goes in for x, right? If -1 goes in for x, denominator, it goes to 0, right? But with what's in the numerator, we can cancel that out and eliminates that, and then we can take the limit of just x minus 1. So if I want to rewrite this to be kind of combined out as x approaches -1, our numerator would be the x squared minus 1 over an x plus 1. And so here's an example of a limit where this critical thinking question they provided to us, where the limit at -1 exists, but it's also undefined at -1. Again, there are many answers here for this, but here is just one example. We're given this critical thinking question. Give two values of a where the limit cannot be solved using direct evaluation. Give one value of a where the limit can be solved using direct evaluation. Well, the main thing I'm looking here, when we're given the function limit as x approaches a of x over 1 over -2 plus x plus 1/2. So what I'm really looking for here is, I'm going to first look for where we cannot solve by using direct evaluation. And that's going to occur when this denominator is equal to 0. So I'm going to look at just the denominator here. We have a 1 over a -2 plus x plus a 1/2. Okay. Well, what happens when I plug, 2 in for x right here? If I plug a 2 in for x, right, what do we get? We have a 1 over a -2 plus 2, with the 1/2 right here. Well, 2 for that x causes this to go to 0 right there, right? And we cannot divide by 0. So that's one value here, as a is equal to 2, where we cannot really solve by direct evaluation. Now what happens when we put a 0 in? So this is when a equals 2. What happens when we put a 0 in for x? Okay, or our a value is 0, right? We would have 1 over -2 plus 0 plus 1/2. But again, we would have 1 over, -2 plus 0 is -2 plus 1/2, when that becomes to 0 in general. -1/2 plus 1/2 is 0. That would cause this whole denominator to equal to 0, and again, we cannot divide by 0. So our two values using, we cannot, so this would be no direct evaluation would happen at a equals 2 and 0. We cannot plug directly in those two values because it causes a division by 0. But what about direct evaluation? What can a equal? Well, at this point, we've actually exhausted all the possible parts of a rational function here where we would be dividing by 0. So, by our rules and what we know about rational functions, not irrational, rational functions, is that we can really plug in any other number here. And it would work. So pick like 10, and it'll be fine. And that would for direct evaluation, but any other number besides 2 and 0 would work. That's it. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.